Okay, so yeah, sorry for the silence. It was testing basically whether there's still like the whirring sound that I had before. I recut lecture three so that it should be on YouTube now. Um, an issue before was that for whatever reason, of all the videos I've recorded since the shutdown, that was the only one that had been blocked due to the automated, copyright music sniffer bot on YouTube. So all of the others had just been demonetized, which is fine, obviously. Not all of the others, maybe like four or five of the others. But anyway, like I said, the music was to solve the the whirring sound, but it'll return next time. So anyway, I didn't get to do Tuesday's lecture due to internet issues on Tuesday, and then I've been having issues. So I was having issues recording stuff yesterday. I only managed to get one thing done. So anyway, so I will upload supplemental lectures, and also I'm gonna make big updates that will be the last updates. I know that I've been saying that for like a week and a half now, but I'm gonna make some changes to the syllabus that are going to be like the final changes. So I'll save you all the time and put that in a post so that it's all in writing and you don't have to listen to me saying it here. So anyway, so keep an eye out for that. Anyway, okay. So what I wanted to do was prove the Archimedes-Riemann theorem, which is something that I didn't get to do last time. So Archimedes-Riemann theorem was our criterion for a function to be integrable. So let me move this up. So the Archimedes-Riemann theorem says that if you have a bounded function, then it's integrable if and only if there's a sequence of partitions that have this property. Okay, that the limit as n goes to infinity of the upper and lower Darboux sums associated with those partitions is zero. That the limit of their differences is zero. And then in this case, what is true is that the limit of the lower Darboux sums for such a partition is the lower integral that we define, and the limit of the upper Darboux sums is this upper integral. And remember that our definition of integrability is that these two integrals are the same, and we call that common thing the integral of f on the closed interval a to b. So this is the Archimedes-Riemann theorem. So I didn't get a chance to prove this. That's what I'm going to do now. So in order to prove this, so this is an if and only if statement. It turns out the backwards direction is actually not so bad. So I'm going to assume that there is such a sequence and show that it means that my function is integrable. So that direction is pretty quick. It's the other direction that takes a little bit more work. So proof. Of Archimedes-Riemann. So suppose there exists a sequence P sub n of partitions. We'll call these partition sequence of partitions that exists having that property. Oh, I'm off screen. So we'll call a sequence of partitions having this property an Archimedean partition, or an Archimedean sequence of partitions. So suppose there exists a sequence of partitions having the specified property. So this is the backwards direction. Okay. We wish to apply previous lemma to these partitions. What do I mean by the previous lemma? So, going back, there was a lemma that we didn't actually do the proof. I said it was mostly bookkeeping. We did the proof of like 2 of these inequalities. So the lemma in question is this one at the bottom of the page. So this lemma is a collection of inequalities for these upper and lower Darboux sums for some partition. So this was actually true of any partition. These are inequalities involving these upper and lower integrals. Okay. So in the textbook, this lemma is called lemma 6.7. So it's a list of like 4 inequalities involving these things. So these are the inequalities in question. Okay. All right. So we wish to apply those inequalities. All right. So in fact, plugging in some p sub n for p in the relevant inequalities yields the following. So this is looking back at this page. This is inequality 2 that I'm about to use. Okay, so I'm going to use inequality 2 where I substitute p sub n for p here. Okay. All right, so plugging this in, taking limit, what do I get? I get that the upper integral of f minus lower integral of f. This is greater than or equal to 0, and it's less than or equal to the limit as n goes to infinity of the difference upper Darboux sum of f for partition p sub n minus lower Darboux sum of f associated to partition p sub n. Okay. But we know what this limit is. We're in the converse, or we're in the backward direction, meaning that we're actually assuming that this limit is 0. So I have quantity, and it's less than or equal to 0, or sorry, greater than or equal to 0, and also simultaneously less than or equal to 0. So the upper integral is equal to the lower integral, and thus f is integrable by definition. Okay. All right, so, oh, I missed out on an is there. Okay, so that takes care of the backward direction. The forward direction requires slightly more work, but it's not too bad either. So what's the forward direction here? So now, rather than assuming that there exists a sequence of partition having this Archimedean property, I'm going to assume that my function is integrable and show that there then must exist this sequence. So let's do this. So let's say assume our f is integrable. Okay. Then by definition, we have that the lower integral of f is equal to the upper integral of f, which we're calling the integral of f itself, right? Okay. Okay. So fix some n in the naturals. Okay, so fix some index n. All right. By definition, of, for instance, the lower integral. So by definition of this lower integral, this thing, the lower integral of f, is the least upper bound. All right, it's the supremum on the lower Darboux sums. So it's the least upper bound of the set of lower Darboux sums for f. Okay, thus, if we take the number which is this least upper bound and subtract from it 1 over n, so you've seen this trick before, right, when we were dealing with sequences previously. So what can I say about this quantity? Well, if this lower integral is the least upper bound for the set of lower Darboux sums, then this quantity being strictly less than, so for some fixed n, this is definitely less than that. This is not an upper bound, right? So this is not an upper bound for the collection of lower Darboux sums. Okay, but think about what that means. That means that there must exist some partition, right, for which the lower Darboux sum is bigger than this, right? i.e., there exists some partition, say P prime, for which this lower integral f minus 1 over n is strictly less than the lower Darboux sum for f associated to that partition P prime. Okay. Okay. Now note that this computation is something that only relied, so starting here, right, so ignore this first sentence for a second. Starting here, starting with fix and n, everything that I did here works whether or not f is integrable. So I didn't use the fact that f is integrable here. Recall that the lower integral for f is defined whether or not f is integrable or not, right? Because it's defined as this supremum of this collection of Darboux sums. The Darboux sums, I can also define those, right? So the point is that, and that supremum always exists, right? Because this is a collection of real numbers ultimately. So what does this mean? So long as, sorry, I should say that so long as that set is actually bounded, and it is for a bounded function. Okay, so that's why we're assuming the function f is bounded. So for a bounded function, sets of lower and upper Darboux sums are always guaranteed to have their sups and infimums, and because of that, the lower and upper, these upper and lower integrals are defined always. And so, getting back to what I was saying, what this means is that everything I said here doesn't have anything to do with the fact that f is integrable, but I want to use that. I'm in the direction where I'm needing to use that f is integrable. And so how do I use that? Well, here I have this estimate involving the lower integral of f. And since I know that f is integrable, this lower integral of f is actually equal to just my integral of f. Okay, and so I can substitute that in for this lower integral. So, I should say, thus, the integral of f on AB minus 1 over n is strictly less than L of f p prime, right? So the lower Darboux sum associated, or for f associated to this partition p prime. So similarly, we can follow this through instead of subtracting 1 over n. We can add 1 over n and talk about the upper integral. And so similarly, we can say that this integral of f plus 1 over n is strictly greater than the upper Darboux sum of f on some partition p prime. So for some partition, or sorry, p double prime. Let's go through why this is. Okay, so maybe I'll put this in parentheses, right? So the upper integral of f is a greatest lower bound for the collection of upper Darboux sums of f, i.e., this upper integral of f plus 1 over n is not a lower bound for that collection, i.e., there exists some partition p double prime such that the upper Darboux sum on p double prime must be strictly less than the upper integral of f plus 1 over n. But again, since f is integrable, this is actually just my integral, right? But f integrable implies that I get the exact same estimate where I've replaced my upper integral with just the integral. Okay. And so I have two estimates. There they are. Okay. What is the idea? So I have some partition p prime for which this is true. I have some other partition p double prime for which this estimate is true. And now I think to myself, I want to come up with a partition that has these two estimates in common, right? I want to come up with a partition for which these two estimates hold simultaneously. Well, I already gave away what it is I'm going to do here with the word I used. So what if I consider a common refinement of p prime and p double prime? So idea is consider a common refinement of p prime and p double prime. Okay. i.e. both the above boxed estimates will hold for. Remember, when I say a common refinement, really there's the common refinement that I'm thinking of, which is just the union of those two partitions. Okay, so that will work. That's a crude way of just slapping them together and doing it. So call this common refinement P sub n. substituting P sub n for P prime and P double prime above, since it will hold, both of these will hold for this P sub n, since it's a common refinement of P prime and P double prime. So substituting P sub n for P prime and P double prime above, we get the following. We get exactly what we want here. We get that if I subtract these two things, then these two things are strictly less than, looking at these two estimates, I have the integral from a to b of f plus 1 over n minus the integral from a to b of f minus 1 over n. But this is just so the integrals cancel out, and I have 1 over n minus 1 over n. This is 2 over n. And so for any n here, right, I fixed an n when I began this process. So for any index n, I have this bound that this difference, the upper Darboux sum of f associated to p sub n minus the lower Darboux sum of f associated to p sub n, this is between, so it's greater than or equal to 0, and it is strictly less than 2 over n. Thus, what can I say about the limit? It must be 0 by squeeze theorem, if you like, right? Or just the thing that we use all of the time whenever we're talking about limits. Okay. So we have shown then that this if and only if part of my Archimedes-Riemann theorem is true. So that holds. But the Archimedes-Riemann theorem made one more thing. It made one more claim. Let me grab my sheet over here so that I don't have to keep writing stuff. Where did I put it? Ah, there we go. Okay, so going back here, I have shown that, so the first thing I showed was that if there existed this sequence of partitions such that this was true, then f was integrable. The second part I showed if f is integrable, then there exists a sequence of partitions like this, right? We found it as the common refinement of the p prime and p double prime found using that process. So in this case, I have these two facts. So I haven't shown these things, right? I haven't shown that these limits are actually equal to what I'm claiming here. So that's the last thing I have to do. I'm almost done. I'm done using previous lemma inequalities. That's what I will say. Okay, so I will leave it to you to investigate why that is. Recall the previous lemma inequalities that I'm referring to. In the textbook, like I said, it's called lemma 6.7. Here, when we did it, I wrote it out in this way. It's this list of inequalities. So using these inequalities, I claim that this last bit about those limits is obvious. Okay, so you should have a look at that. All right, so that's it. We've shown the Archimedes-Riemann theorem. All right, so what does that mean? Well, it means that now we have this nice criterion for integrability of a function. And we're going to see how that applies to some fairly large class of functions. First, I'm going to give a couple of definitions because they're going to be useful later. Definition, we call a sequence of partitions P sub n Archimedean if it satisfies the condition in the Archimedes-Riemann theorem. Okay. i.e. if f is bounded on closed interval a to b, and then the limit as n goes to infinity of upper Darboux sums of f associated p sub n minus lower Darboux sum of f associated p sub n is 0. Okay. So in this way, there is a convenient way to reword the Archimedes-Riemann theorem. So you could reword it like this. So a bounded function f is integrable if and only if there's an Archimedean sequence of partitions for f on its domain. Okay. All right. And so what this means is that if we want to know whether or not some given function or type of function is integrable, what we need to do is construct an Archimedean sequence of partitions. Ideally, right? That's our idea. So again, to make our life easier going forward, I have a couple definitions. You're actually familiar. You're familiar with one of these things that I'm going to say, at least, and you might be familiar with the other one. So here's a quick definition. It's the definition of a regular partition. And you probably know what's coming the second I say that. So for a natural number n, the partition, I'm always throwing extra t's in there. The partition P, that's using normal partition notation, looks like this. So this partition of the closed interval a to b, defined by x sub I is equal to a plus I times b minus a over n for I between 0 and n, is called the regular partition of AB. Okay. Into n intervals, if you like, or n subintervals. Okay. You should note immediately what is the key property that this irregular partition has. This might have previously been called an equidistant partition, right? It is a partition where each of the subintervals has the same length, right? B minus A over N. So note each partition interval or subinterval of a regular partition has length B minus A over N. So the number of partition intervals, right? The number of subintervals in your partition is what actually determines this length. All right, so you've definitely seen this a bunch before, right? So the idea was that all of these quantities were defined for generic partitions, but of course it's a lot more convenient and it's a lot nicer if you can assume that a partition is arranged in such a fashion. Right, so regular partitions are nice. One more definition and then we'll move on. So another definition, which is gap of a partition. So what's the gap of a partition? So for a partition P using normal notation, For a partition P, usual notation. Maybe it took me as long to write that as just writing it out. Define the gap of P to be the length of its largest partition interval. i.e., gap P is defined to be the max over I of x sub I minus x sub I minus 1. Okay. Okay. So the gap is the maximum over the entire partition of this difference, which is, of course, the length of each partition interval. So it's just the maximum length of all the partition intervals. Okay. All right. Quick note. So your textbook makes this observation. So note that gap P is less than epsilon if and only if each partition interval of P has length strictly less than epsilon. Right? This is just a nice organizational definition that allows us to say a nice thing about a partition without having really long word salad. Okay. So, following fact is very important. Probably should call it like a theorem or maybe even a lemma. The textbook calls it an example. I'm just going to call it a fact. A monotone function f on AB is integrable. Let's assume it's monotonically increasing. A similar argument is going to show that this is the case even for a monotonically decreasing function. So assume monotonically increasing. Okay. So we wish to use the Archimedes-Riemann theorem to show this. Okay, so here's my important fact. This is going to get us that a lot of things are integrable just right out of the gate. Okay, so this is an important thing to know. It's also a really good example of how to use the Archimedes-Riemann theorem. So, let's say let P is x naught to x sub n be a partition of the domain of F. Okay. Note that since F is monotonically increasing, then for all I and partition interval or subinterval x sub I minus 1 to x sub I, we have the following. Little m sub I, which is the defining thing for our lower Darboux sums, this, of course, is defined to be the infimum of, so this is the infimum of functional values such that x is in this partition interval in question. Okay, so this is how m sub I is always defined, but for f monotonically increasing, we know where the smallest of these values is going to occur. Right? It's always going to occur at the left endpoint. This isn't anything amazing. This was actually something we talked about right out of the gate when I defined upper and lower Darboux sums. So remember, I did this whole discussion of why upper and lower Darboux sums are nicer theoretically to deal with than left and right Riemann sums. One, because upper and lower Darboux sums, you know automatically that a lower sum always underestimates and upper sum always overestimates. They have really, really nice properties, whereas a left and right Riemann sum doesn't necessarily do either of those things, right? It depends on the properties of the function. And so while it's nicer if you're going to be computing Riemann sums by hand, it's much worse mathematically, like in terms of the properties that it has. But we see here that for a monotonically increasing function, my lower Darboux sum is going to be the same as a left Riemann sum. Right? That is a Riemann sum where all of those rectangles to determine the height, what I'm actually doing is always picking the left endpoint. Similarly, before I even get to it, you know that what is also true is if my big M sub I that defines my upper Darboux sums is the supremum of this same set, since f is monotonically increasing, this sup is going to occur at the right endpoint. And so for a monotonically increasing function, upper Darboux sums are the same as right Riemann sums. Now, I can pause here for a second. If f was monotonically decreasing, how would this change? For a monotonically decreasing function, the lowest functional value on the subinterval would occur at the right endpoint. And so for a monotonically decreasing function, a lower Darboux sum is going to be the same as a right Riemann sum. Similarly, for a monotonically decreasing function, the upper Darboux sum is going to be the same as a left Riemann sum. Okay. All right, so now that we've seen what that means, then for n some natural number, let P sub n be the regular partition of the closed interval a to b into n intervals of equal length b minus a over n. Then, what do I have? So, if I look at the difference between the upper and lower Darboux sums associated to this regular partition, I get, just by the definition of these things, right? This one involving big m sub I, this one involving little m sub I get that this is a sum equals 1 to n of big m sub I minus little m sub I times x sub I minus x sub I minus 1. But for a regular partition, we know what this is. Right, so this is the sum from I equals 1 to n of big M sub I minus little m sub I times b minus a over n. Okay. We can factor this out because this no longer depends on I. And now we know what these m sub i's are. So this is actually equal to b minus a over n times the sum from I equals 1 to n of big M sub I minus little m sub I. Again, we know what these are. This is b minus a over n times the sum from I equals 1 to n of f of x sub I minus f of x sub I minus 1. But this sum telescopes. All right, this is a telescoping sum. So this is going to give me f of b minus f of a. That's the end point. This is the starting point. Okay, so this sum telescopes in an obvious way. And so that is equal to b minus a over n times f of b minus f of a. Okay. Thus, why are we done now? We have this depending on n in a way that is going to make what I write now obvious. Thus, the limit as n goes to infinity of upper Darboux sum associated p sub n minus lower Darboux sum associated p sub n is what? Well, it's the limit as n goes to infinity of this quantity, b minus a over n times f of b minus f of a. But b minus a and f of b minus f of a don't depend on n at all. So really this is just thing that doesn't depend on n times the limit as n goes to infinity of 1 over n. This is 0. Thus, p sub n is an Archimedean sequence of partitions for f, i.e. f is integrable by Archimedes-Riemann. Okay. Okay. All right, so this is certainly a nice way of dealing with these sorts of questions. Now we know that a monotone function is actually integrable. So that's nice. Not quite the generality we're looking for, right? You might recall at the beginning of chapter 6, I mentioned one of my main goals was showing that continuous functions were integrable. But this is a step in the right direction. Okay. And speaking of steps, I'm going to define a step function. You already know what a step function is, but I'm going to give the explicit definition. So a function f defined on closed interval ab is called a step function provided there exists a partition. Textbook calls it P star, which is z naught to z sub k of its domain AB, and numbers c sub 1 through c sub k such that f of x is equal to c sub I for all x in z sub I minus 1 z sub I. So you know what this means. A step function is exactly what you think of when you think of this piecewise defined function. It's piecewise constant, if you like, right? And so there are actual honest-to-God pieces, right? You can't, right? Every function is pointwise, every real valued function is pointwise constant, right? That's not quite good enough. There's too many points, okay? So what we mean is that there are a finite number of pieces. These pieces are thick, right? These pieces are actual subintervals. And on each of those pieces, this function is constant. These constants can vary, of course. So this is exactly what you think of when you think of a step function. So my reason for saying this is another fact. And you might view this as kind of less surprising than the thing we just proved. It's a little bit more involved to show that this is the case, and I'm going to leave it to you to do that. I can tell you what you can look up in order to do that. So here's a fact. Step functions are integrable. So let me just explain a little bit what I was saying before. Because a step function is essentially just a bunch of piecewise constant functions, and since constant functions are integrable, that's easy to show. You might not be too impressed by this fact. Also, thinking back to the very beginning, the original intuition for this, if you have a step function and you wanted to compute the area underneath it, the fact that it's not continuous, you might at first think that there's an issue, but if you thought about it for a second and you filled in the rectangles, in fact, I want to say I even have a picture of something we did when we were first talking about this stuff. Maybe not. Maybe I threw it away. But basically, notice this need not be continuous, and yet it's still integrable. Okay. In fact, I made no mention of continuity for my monotone function either, and you can think about why that is. So proof for this is page 147 in the textbook. So you can have a look at that. It makes use of this gap of a partition that I defined. Okay, so finishing up this section, and then I know I titled this lecture, I think I titled this lecture Applications or Properties of the Integral. So I'll get to that stuff soon. We'll be doing that stuff actually very soon. And I know I still owe you a lecture from earlier in the week that I'm gonna record sometime before Friday evening and post it. So I'll do that. But finishing up this section, the last thing I wanted to talk about, I didn't really talk about Leibniz notation that much when we were talking about derivatives, but finishing up this section, reminding you Leibniz notation. Of course, I don't need to remind you of too much here. I'm sure that everybody knows what I mean when I mention Leibniz notation in this way, right? Of course, like the intuitive description, you were given for this dx was that it was, the thing in the limit if you thought of the length of the subintervals being delta x, right? Change in x. Then it's just limited to d, and that's fine intuitively. Unfortunately, if I want to be, it's just one of those things. It's kind of like orientation is another example of one of these things where intuitively what's going on, like your idea of it is not that muddied at all, and it's pretty simple to describe. But if I want to be real rigorous about like what I mean when I slap down this integral sign, and it takes a little bit more words to talk about, and so I'm not going to get into it. But everybody's familiar with this notation, and so I want to use this notation to compute an example, right, which is compute this thing. Okay, the integral from 0 to 1 of x squared dx. All right, and I want to compute this using my definition of integral, right? Using my definition of integral. Okay, so not how you would normally do it. Now, we know if this notion of how we've defined the integral is going to match up with everything else you know what this has to be, right? We know this needs to be, right, and I put needs in quotes here. What does this need to be? Well, the integral of x squared, if we do this by antiderivative, this would be 1/3 x cubed evaluated from 0 to 1. Well, that's 1/3, right? This needs to be equal to 1/3. Okay. All right, so recall, we'll need this. Recall that the sum from I equals 1 to n of I squared has a closed form formula. This is something you can prove with induction. This is n times n plus 1 times 2n plus 1 over 6. All right, this is literally like the second thing you prove with induction ever. Okay. All right, so here's this thing, this formula. Okay, now for each n in the naturals, let P sub n be the regular partition of 0, 1. Into n subintervals, or partition intervals, of equal length. Okay. Now, in our example of the monotone function, we showed that this forms an Archimedean sequence of intervals. So this is an Archimedean sequence of partitions, sorry. Why does this apply? Well, note x squared is monotone on the interval 0 to 1. All right. Okay, so that's important. All right. Furthermore, maybe I probably should have mentioned this at the beginning. Since this is monotone, it's integrable, right? Thus integrable. And so we're not doomed to failure in the first place. So I should have said that at the beginning, but this is what we know. This is an Archimedean sequence of partitions. Thus, for instance, by Archimedes-Riemann, this integral from 0 to 1 of x squared dx is actually equal to the limit as n goes to infinity of the upper Darboux sum of f associated P sub n. All right, this was one of those last things that Archimedes-Riemann stated. Okay, and so if I want to compute this, I can compute it as a limit of these upper Darboux sums. Okay, now note that this big M sub I is, as before, this is the soup of functional values on the subintervals in question. But what is this? This is just f of x sub I, right? It's the value of f at the right intervals, or at the right endpoints of these things. Okay. Okay, well what is this? My function is x squared, so this is just So what's my functional value here? Well, this functional value is I squared over n squared. And x sub I minus 1, x sub I, or rather the length of this thing, sorry, this difference I should say, is 1 over n. All right, it's b minus a over n, so b minus a is 1 minus 0 over n, so this is 1 over n. Okay. All right. Okay, so what does this mean for my upper Darboux sum? So my upper Darboux sum is the sum from I equals 1 to n of big M sub I, x sub I minus x sub I minus 1. But I just computed these things, so this is the sum from I equals 1 to n of I squared over n squared times 1 over n. So I can get rid of everything that doesn't depend on I here. So this is 1 over n cubed times the sum from I equals 1 to n of I squared. So here's where knowledge of that formula comes in. So this is 1 over n cubed times n plus 1 times 2n plus 1 over 6. All right, so I have this rational expression in n, thus the limit as n goes to infinity of the sequence of upper Darboux sums is the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2 n plus 1 over 6. You have a rational expression here in n. So polynomial over polynomial. You know how this works. Since degree of the top is 3 and degree of the bottom is also 3, the limit as n goes to infinity here, right, goes to the ratio of the leading coefficients. So that's 2n cubed over 6n cubed. So this would be 2 over 6, or 1/3. Thus, the integral from 0 to 1 of x squared dx is, this is the limit as n goes to infinity of this sequence of upper Darboux sums, and that's 1/3. Okay. So this does check out in the exact same way. All right. Okay. So that is how this works, and this is one way of applying Archimedes-Riemann to see that our definition here matches up with what you know, right? Okay. So I'll mention the next couple of things that I want to talk about, and I'll prove them next time. So it's all of the properties of the integral that you're familiar with. So next time we prove additivity, monotonicity, and linearity of the integral. So additivity, of course, is that you can split the integral, right? You can split the interval that you're integrating over into two pieces, compute the integral of the pieces separately, sum the results, and that is your integral over the entire interval. So that's additivity. Monotonicity is that integrals respect inequality. So if you have a function dominated by another function, then the integral of the dominant function will dominate the integral of the other function. And then linearity is exactly, you know what linearity is. So those three properties are very important for the integrals. So we'll do all of that next time, and may even be able to finish this proof that continuous functions are integrable. So that's the idea. Going forward, the plan is to give full treatment of Chapter 6 and Chapter 8, and as much of Chapter 9 as we can. So we're not going to be able to cover as much as we would have normally covered without shutdown, but so that's unfortunate, but that's just how it's got to be. So so going forward, like I said, I owe you all at least like a lecture and a half, maybe 2 full lectures. I know one of the lectures I posted was really almost like 2 lectures in terms of content. So so I owe you all at least 1 lecture, and so I'll take care of that soon and let you know. Like I said, keep an eye on the Elm's announcements, because I'm gonna make a few final changes, and that's gonna be it. Okay. So anyway, so that's the plan, and I'll let you know about all that stuff. There's no due dates or anything coming up soon you have to worry about. Everything is going to be due by the end of the semester. So like I said, I'll enumerate all of that in my Elm's announcements. But anyway, so take care and see you all next time.